being here, guys. It's a smaller crowd today, but we're glad you're here. We're just going to do the same thing that we did last time, where we're going to walk through the practice exam that we sent out. We're hoping that this is helpful for the exam. We have no idea what the exam looks like or what's on it. Jocelyn is writing a new one. So, we just kind of wanted to warn you, make sure that you are also studying just like the general concepts of what we've learned the past few weeks, because we don't know. We knew how similar last exam was to this. We don't know how similar this one is. And so we're hoping this will be really helpful, but just, don't expect it to be comprehensive today. But this is what Jocelyn asked us to review. So
yeah. I feel like that should at least give you a little bit of comfort, is that Jocelyn still felt like us walking through this would be the most helpful thing for you in this review. But I think there will be fewer repeat questions than last time.
And maybe we'll be wrong.
Yeah, it's true. We could be wrong. It's all speculatory, speculation. I also have had questions from a few students about the length of answers. There was a lot of variability in answer length between students on the last exam, and I thought it was really helpful. Something that Jocelyn shared with us last year is that if you're printing out the exam and writing down your answer, the amount of space that's provided should be enough space to answer the question sufficiently. So if you are typing up a page or two in response, or like a mini essay, that's probably too long. But if your answer is a single sentence, then it's likely too short. So if that's helpful for you, that's just a pointer from Jocelyn. But I think the instructions for the exam are the same as the previous one, so we won't go into those this time. But you can just print it or write your answers on a separate sheet of paper or type out your answers again, whatever you prefer. And with that, do you have any other pointers, Julia?
No, you guys did great on the first one, so just keep it up.
Yeah,
everyone did awesome. So this will be like the same kind of format and everything, probably same link. Okay, so we're gonna walk through the questions. Feel free to ask a question at any time. Hopefully we'll have some time at the end for just any other questions. We're going to spend the bulk of the time on part 1 and then the first question in part 2. I have already made a video demonstrating the last question if we don't get to it. So you guys will have that. Okay. You're welcome to type on there if you want to. I'm just going to be using these.
I think I will.
Okay.
So
Hannah's going to type some answers up there while we talk through it. So okay, we're just going to get started. So starting with the short answer questions, our first question is, why is multiple regression useful even when we are interested in only one of the explanatory variables? I'm just curious first, before we answer this for you, what would you guys say? Yeah, totally. Yeah, I mean, put simply, that is why. Basically, one of our assumptions says that our explanatory variables are not supposed to correlate with anything in the error term, right? And so just like you said, one way to address that is to control for anything that could be in the error term that could be related, right? So even though in multiple regression, we're still isolating the relationship of each variable, when we have multiple variables in, we're seeing what is that relationship for each variable with everything else held constant, which allows us to get closer to that assumption being met. I'd leave out that last sentence.
Yeah, that's great.
I don't think that's true. Yeah. Perfect. Okay. Any questions on that? You guys you've known that. That's been a principle throughout this class. Okay, so when we're working with qualitative explanatory variables, why can we not just put in a qualitative variable with values 1, 2, 3, 4? Does anyone know? What's the issue with doing that for explanatory variables? Yeah.
Those numbers don't actually have meaning.
Exactly. Yeah. And so what Hannah's going to type here, yeah, I mean, however you want to answer it, but really it's important to know here the difference between your quantitative information and your qualitative information, right? In quantitative explanatory variables, our magnitudes matter, the ordering of the numbers matter, the values of the numbers have practical meaning, right? We have units. When we're working with qualitative variables, that's only capturing information on non-numeric characteristics and categories. And so when we put it in as 1, 2, 3, 4, Stata tries to treat that as, oh, these numbers are meaningful. There's an order here to these numbers. There's a magnitude to these numbers. And that's not true for qualitative, right? They're just categories. So that's why, what would we do instead? Rather than putting it in for 1, 2, 3, 4, how would you represent qualitative variables in your model?
You choose a comparison and then everything, and then you put in one less than the number of things you have, and you don't put in the limits.
Right.
That's your comparison.
Yeah, totally. So you take each group of that qualitative variable and you create a dummy variable for it, right? Which is a 0 or a 1. 1 meaning yes, 0 meaning no. And you're right, when you want to put all of them in your model, you can leave one out because that will be your reference group. Right? That will be your intercept value. So you can answer that question by saying, we create categorical dummy variables with binary outcomes to measure each group. However you want to say that is totally fine, as long as we can see that you understand that difference between the quantitative and qualitative. Okay. All right, moving on to number 3. What is a standardized beta? What does it mean if our coefficients or our betas are standardized? Any ideas?
Means the numbers are in reference to standard the
Units are in standard deviation.
standard deviation.
Yeah, exactly. I mean, the answer it has here is a standardized beta is the estimated coefficient that results from a regression when our variables are standardized. So our variables have to be standardized first before they're put into the model. And I think in class, we've really just been working with unstandardized results, which is totally fine. But it's important for you to know what it means for something to be standardized. And you're right. The units of a standardized beta or anything that's standardized are standard deviations of our outcome, of our Y. So let me just, make sure. So the coefficient, when it's standardized, it compares the strength of the effect of each individual independent variable. So that's kind of answering that second question or that third question. Why do we sometimes use standardized coefficients? It's because unless our variables are standardized, we can't compare them with each other if they're in different units, right? So let's say that we have income and we have life satisfaction or something as 2 explanatory variables. Our coefficients, our betas for those, if they're not standardized, are going to depend on whatever unit that those 2 variables are in. So if we want to directly compare the 2, we want to standardize it, put it on the same playing field. So that's why we use standardized coefficients. It allows us to see which covariates have the strongest connection to Y. We want to compare between explanatory variables.
I think this was actually a question on the first midterm, and lots of you, well, all of you did really well. And so you can also go and reference your answer for midterm 1. But
yeah, you had some
perfect
about standardizing. Yeah. But yeah, it's just important to know the units are in standard deviations of Y. And the way that we interpret it is a 1 unit standard deviation increase in X relates to blank standard deviation change in Y. That's the difference. We're just talking about standard deviations. Any questions on standardizing?
One standard deviation in X is it's X. It's whatever.
Is beta standard deviations in Y. Exactly. Yeah.
Because of both.
Yeah, they're both
perfect.
They're both in standard deviation, right? The unit of the beta is standard deviation of Y.
You want me to add anything else to that?
Maybe just this part.
Yeah, you can keep going and I can type that
Can you
too.
say what you were saying about how you interpret it?
Yes, and she's gonna type it as I say it. So
Thank you.
the units of the beta are standard deviations in Y. The way you interpret the beta is just like we do with other regression. A 1 unit standard deviation change in X is related to a beta, whatever that is, standard deviation change in Y. Perfect. Okay. All right, let's move on to question 4. Okay. This is a question that wants you to mark all that apply. So looking at the following regression equation, this is a very familiar equation we've all seen before. So we've got y equals our intercept plus x1 beta 1 plus x2 beta 2 plus u, which is representing our error here. So we want to look at that beta 2 there, and we want to mark all that apply to the interpretation of beta 2. Okay, so think in your mind what you would say for this, and then I'm going to kind of walk through a way to think about this that'll be helpful. This is the extra.
Oh, this is the
Mhm.
extra, yeah.
Yeah, we're in question 4.
Thank you.
No, you're good. Welcome. Okay, so this is how I would walk through this question. First, we know right off the bat that we can eliminate A, B, E, and F, because all of those are talking about the effect of Y on X, which is what we're never talking about in regression, right? Y is always our outcome. And so when it says the estimated effect of Y on X squared or on X2, the estimated effect of Y on X2, and then E and F say a 1 unit increase in Y will increase X. That's never what we're interpreting from regression. So we can look at that and be like, oh, no, we are never looking at a change in Y affecting or relating to a change in X. So we can take those off. So that leaves us with C, D, G, and H. Okay. What is different about C and D? I mean, if you were to compare C and D, which one is more accurate for this equation and why?
Is it? Because there's no.
Close. So if we look at the equation here, we actually do have 2 different betas, right? We've got an x1 b1 and an x2 b2. So your logic is right, but switching it. Yeah. Is that actually we would want to eliminate D, right? Because we are holding all else equal here because it's a multiple regression, right? The only case D would apply is if we didn't have multiple variables.
Wait, but it's all that applied, is it not including D, because that does apply, you just are adding something else onto it.
Nope, it would just be C, because D is technically not correct because it's incomplete to talk about the effect of X2 on Y without saying that we're holding the other things equal. That was actually something I was grading your guys' problem sets 5 yesterday. That was a note that I left on almost everyone's homework. Didn't take off points for it, but keep it in mind for the exam. Also, you don't have final grades for that yet, but you will soon. Keep in mind that whenever you're interpreting a beta or a coefficient from a multiple regression, you've got to include that idea that, you know, if we're saying, okay, a 1 unit increase in X is equal to this change in Y, if it's a multiple regression, you've also got to include holding whatever else constant. Because it's not technically I mean, I counted it because it makes sense, but it's not technically the most correct way to talk about regression if we have multiple variables in the equation. And so like in this equation, beta 2 is the effect or the relationship between X2 and Y holding X1 constant, holding all else constant, okay? That's important for multiple regression. So just remember that for your interpretations.
Another really brief note that I will make is that you're only really going to be interpreting the coefficients for your research question of interest. So I wouldn't bother in your papers or in your assignments interpreting the beta coefficients for all of the controls separately. That's another thing I've seen in a lot of homework is that it won't mention that holding all else equal or holding all else constant, like Julia mentioned, but then it will proceed to, the paragraph will proceed to interpret the beta coefficients for all of the individual controls. You do not need to do that. We want to know what is the estimated effect of X, your primary independent variable, on Y when holding those controls constant. So
Unless the question specifies.
unless the question specifies on your homework, but yeah, go ahead, Haley.
Sorry, remind me how G or H would it be?
Good
We haven't
question.
got
You're
to
getting
those
ahead
yet.
of us.
Yeah, no, you're
Let's
good.
talk
Let's
about
talk.
those. Yeah, what would you guys say? Which one, knowing what we just talked about with C and D, which one is more correct, G or H? Yeah, correct.
Perfect.
And so for this question, you would, if you got a question like this, the answer would be C and G are the two that are right. Yeah.
Looking at this interleave B2, does that mean B1 is considered a constant? Even though you would normally put in that place, like your explanatory variable?
Yes. Yeah, like you would still have your if we were to plug in all of our numbers, you would still have a number for B1. It wouldn't be 0. But when we're interpreting B2, just B2, we're isolating it. So we're holding B1 constant. We are saying that when we're interpreting B2, we're pretending like B1 is 0. But in your equation, like, yeah, you would have a beta 1 coefficient, but it's just for when we're interpreting what each one means. Does that make sense?
I think so.
Okay.
Yeah.
Okay, moving on to 5. We're not going to answer this one because this was actually on verbatim on your previous exam, and you guys did great. It's asking, how does the R squared change if we change the units of measurement on a variable from dollars to cents? I'll be surprised if you get this question because you already did, but you guys all had it right that the units of R squared does not change because it's a proportion, right? It is not dependent on the units of the variable. So we'll go right into question 6. Why do we often look at R squared bar, which is the adjusted R squared, rather than just R squared? Does anyone remember this from class? Yeah.
Because it includes an adjustment for how many variables you're including.
Exactly. Yes. R squared will always increase when you add a new variable to your model every single time, because it's a measure of the explanatory power of the model. It's saying how well are these variables explaining why. And so R squared, no matter what, even if the variables we add to our model aren't important, is going to increase simply because we have more information in our model. So that's why we look at R squared, because R squared is mathematically adjusted. It has this built-in mechanism to detect whether the variables we're adding in are actually important in explaining why. And so R squared might not always go up if we add a new variable that isn't significant or isn't important. So it provides a threshold that must be met in terms of added model fit for a variable to be considered added value. And R squared does not have that threshold. So that one is more accurate when we're building models and adding more things. Yeah.
Wait, sorry, I'm confused. I thought you just said that it does change no matter if it's significant or not, and then you also just said it doesn't change if it's not.
R
significant.
squared does change no matter what.
Which
Adjusted R squared does not. Sorry, I might have misspoke.
Yeah, so
sorry.
so essentially, no, I
think
think you got it right. It is kind of confusing to talk about. So R squared technically goes up with every additional variable that you're including in the model. That's why we look at adjusted R squared, because a penalty, I kind of like to think of it as a penalty. There's like a penalty for every additional variable that you add to the model to account for the fact that R squared would normally be going up with every additional variable. That's why it's called adjusted, because it has that penalty for when you have too many variables in the model. So it's more accurate. Mhm.
Adjusted R squared has a penalty.
Yeah, it's adjusted.
But R squared does not.
Yeah, R squared
Mhm.
will go up no
Okay.
matter what. Adjusted R squared
Okay,
will
okay.
only change if the variables you're adding are important.
Mhm. That was a good way to put it, Julia. That was very succinct.
Yeah. That's helpful. I like that word of penalty. That makes a lot of sense. Okay. And then moving to question 7. I'm actually gonna have you not use this. I have a different
Okay.
answer for this.
Yeah, no, that's great.
Okay. This is, you can type this if you want. Let me explain.
I'll wait
first,
till,
and then
yeah.
yeah. Okay. What is the interpretation of a p-value? A p-value is actually one of the most misunderstood things in stats because it's really easy to define incorrectly. So, I'm just going to tell you what it is rather than asking. Okay, so the p-value is basically the probability, and I'll walk through this, but it's the probability of finding our results, our observed results, or more extreme results when our null hypothesis is true. Okay, so what that means is a lot of the time our null hypothesis is that something equals 0, right? It's not always, like when we test whether two coefficients are the same. But I'm just going to use that as an example. If we're wanting to see whether one of our coefficients are statistically significant, then we set that null hypothesis that our coefficient is 0, right? And so the p-value that we get from that test is the probability of finding our actual coefficient or something even farther from 0, if in fact the coefficient is actually 0. Basically, what that means is if our p-value is really, really low, then it just means that it's really unlikely that we found this coefficient by accident. It's really unlikely that our coefficient is actually 0. So if our p-value is less than our alpha, which is basically what we set as like, we're okay with us being wrong 5% of the time, is basically what that means. If the p-value is less than that, we reject the null hypothesis, right? And that's when we would say something is statistically significant. And if it's higher than that cutoff, which is usually 0.05, we fail to reject the null hypothesis, and that's when we would say that something is not statistically significant. Any questions about p-values? Yeah.
Just saying, but like, so let's say I answered it saying something like, oh, it determines the significance of our findings.
Mhm.
That would not be fully accurate because.
That's a part of it, but we also want, we want to know that you understand that interpretation of
It's the
how is it
percentage
doing
of
that?
How likely the null hypothesis is.
So not
Or-
quite. That's where it gets so tricky. The
that's
wording
what-
is so hard.
It's very technical wording.
It's
Yes.
yes. It's the probability of getting what we actually got if the null hypothesis is true,
Okay.
right? Or more,
Mhm.
getting what we got or more extreme. Yeah. That wording is, it's complicated. Yeah.
Does that relate to, you remember when we talked about like the type 1 and type 2 errors?
Mhm.
It does.
Like that?
Yes. The p-value has nothing to do with a type 1 or type 2 error. Our alpha does. So that alpha, and actually you'll see it as it'll often say p equals 0.05 or alpha equals 0.05. That's our cutoff for our p-value. And what the alpha is our probability of getting a type 1 error. And a type 1 error means rejecting the null hypothesis when it's actually true. So it would be like us saying, ooh, this variable is significant when it's not. That's type 1 error. Type 2 error is the opposite. It's saying this is not significant when it actually is. But basically our alpha, that 0.05, is saying we're okay with a 5% chance of getting a type 1 error. We're okay with getting a type 1 error 5% of the time. And so that's our cutoff for if our p-value is anywhere below that, we're going to say we're pretty comfortable with this being significant. Does that make sense? Okay, good question. Yeah.
Hello, everybody. So during the exam review today, I did not finish going through question 1 for the part 2 long answer section. Instead of just instead of going through the first half in the exam review and then the second half here, I thought it would be easier to just go through the whole thing again. So that's what I'll be doing. So here we are. It's the hypothesis testing portion of the long answer section. You're going to open up the smoke data set, and then I won't open this accompanying data dictionary or codebook just because I already have notes in my do file about what the different variables are and how they're measured. But this data set essentially looks at different predictors of smoking. So what we're going to do first is this question says, we would like to understand what predicts someone either being a smoker or not. So whether or not someone is a smoker. And we're going to be generating a binary variable for this. So that's syntax. First, you would generate the smoker variable. And I'm just going to make that equal to 0. And then I will replace that with a number 1 if the number of cigarettes that they smoke in a day is greater than 0. Right now, it's just a continuous variable, like I said, measuring the number of cigarettes that they smoke in a day. So I'm going to run that, and then let's preview our data to make sure that it looks right. So here's that cigs column with the number of cigarettes that they smoke in a day. And then we're going to be referencing this smoker column with that binary variable. So it looks like for those who smoke at all, they are marked with a 1 in that smoker column. So that looks correct to me. And then I think we're also asked to run the tabulate command. So I will run that just to see how many smokers and non-smokers we have in the data set. So it looks like 497 people do not smoke and 310 people do smoke. Awesome. And then we're going to use a logit model to look at associations between different macro system factors and whether or not a person smokes. Because that binary smoker variable is our outcome variable, that does tell us that we're probably going to be running a logit or probit model for this question because those models deal with binary dependent variables. And it does say here that we're going to be using a logit model. So, like I said, smoker, our dependent variable, and then our macro system factors are going to be cigarette price, and then whether or not a restaurant or a state has restaurant smoke bans. So I'm going to type out that syntax. It's just going to be logit, and then we'll put smoker first because that's our dependent variable. And then sig price, and then this variable tells us whether or not there is a ban on smoking in restaurants for a given state. So I'm going to run that. And if you remember, we talked a little bit about this in class, but you actually don't interpret the numbers that you get here just because it's hard to interpret them because essentially they represent the change in the log of a variable. So instead we want to run the margins command so that we can look at marginal effects. This is a lot easier to interpret by making the numbers reflect probabilities instead of a change in the log of that variable. So how you do that is you're just going to type out margins, comma, dy dx, and then a little asterisk in parentheses. Awesome. And the instructions here just said to estimate that model there isn't anything that you need to write here. We'll just review your code in your do file and assess whether or not that was done correctly. So for part C, it's asking you to look at the marginal effects. So that'll be this output right here that we just, for the model that we just ran. And we're going to look at the relationships between those different macro system factors and whether or not someone is a smoker. So first, we're going to look at the price of a cigarette pack. This is measured in cents. And that would be important to know if you were actually interpreting this coefficient right here, but because that p-value is greater than 0.05, then we'll fail to reject that null hypothesis. And we conclude that the price of a cigarette pack is not associated with whether or not someone is a smoker. And that's all you would put there for the answer to that question. However, if you look at whether or not there's a smoking ban in restaurants, that is significantly associated with whether or not someone is a smoker. And you would highlight what that p-value was in the answer to that question. So that's 0.01. So we reject the null hypothesis that there's no relationship between a restaurant smoke ban and whether or not someone's a smoker. So let's interpret this specific coefficient right here, since that was significant. What this is telling us is that when there is a state restaurant smoke ban or smoking restriction, then that's associated with a 10.4% decrease in the probability of someone being a smoker. I'm sitting outside and my papers are blowing away. Just a second. Awesome. So let me show you what the total, like what your complete answer would probably look like. So here I wrote, using marginal effects, we see that a state's cigarette price was not related to whether a person was a smoker, and then I include that p-value. However, having state restaurant smoking restrictions was associated with a 10.4% decreased probability of someone being a smoker at the 0.01 confidence level. So we can move on from that. I did want to make a brief note here that you could also be asked to look at odds ratios on this exam. And so I'm going to run a command for that just so you can see what you would do if you were hypothetically asked on the exam to calculate odds ratios. So I'm going to copy and paste that logit model right here. I'm going to technically put this under there too. So all you would do to look at odds ratios would be comma OR, and that allows you to compare the odds for being a smoker versus not being a smoker. So I'm going to run this. And because a 1 for this binary variable looking at restaurant smoke bans, because that represents that there is a smoke ban, then that's what we're interpreting this odds ratio for. Essentially, how you interpret these odds ratios is a 1 here means that there's an equal probability for being a smoker. Well, here, let me restate that. If this number right here were 1, then there would be an equal odds or probability that someone was or wasn't a smoker, regardless of whether or not there was a restaurant smoke ban. Because this is less than 1, then we know that there's a lower odds. So you're going to subtract that 0.64 value from 1, which gives you a value of approximately 35, 0.36. So if there is a smoke ban, then a person is 35% less likely to be a smoker. If this number exceeded 1, then that would be equivalent to higher odds of that thing. So let's say that this number was 1.64. That would mean that if there were a restaurant smoke ban, then a person would be 64% more likely to be a smoker than not a smoker. And like I said, that's hypothetical. That would be if the number right here were 1.64. So because this is less than 1, then we subtract the 0.64 from 1, and we conclude that when there is a restaurant smoke ban, a person is 35% or 36% less likely to be a smoker. Awesome. So we can move on to the next question, or I guess I can read through this first. So this would be the actual interpretation of that odds ratio if you were asked a question about it. I would say something like, a change in a state's cigarette price did not change the odds of a person being a smoker. People living in states with restaurant smoking bans had 35.7% lower odds of being smokers than people living in states without restaurant smoking bans. And this association was statistically significant at the 5% level, or you could just put the p-value right here, which was 0.01. So that's how you would respond to that type of a question. Let's see what we have next. So now we're going to estimate the model, but we're going to include microsystem factors or factors that are specific to the individual, in addition to those macrosystem factors that we already ran the logit model with. This is another one where you don't have to write out an answer. We'll just look at your do file to see if you ran that model correctly. So I will add those microsystem factors. And as you can see here, we do need to create an interaction term between education and race. That race variable is binary, with 1 representing that a person is white and 0 representing that a person is not white. So I will create that interaction term. We can just call it educ white. And then I'll just multiply those to create that interaction. So we're essentially testing for moderation here. Going to create that variable, and then I'm just going to copy and paste the syntax for my logit model above. And we're not looking at odds ratios here. So let's see. We are doing sig price, restaurant smoke ban again, but then we're adding age, education, race, and that interaction term. Let me see. I want to make sure these are named the way that I expect them to be. Awesome. And then I will add that interaction term, and we can run this model if it'll let me click on it. There we go. Run that model, and then of course we're going to look at margins like we always do, since that makes it easier to interpret these numbers.
Yeah, you talked about them so much.
Great. So we ran that model, and we don't need to type anything for that one. It looks like I accidentally deleted the letter here, but that is a question, or I guess That's part of the actual practice exam, unlike the odds ratio problem that I went through. So this next one, based on results in the previous part, does being white moderate the relationship between a person's education and the likelihood of smoking? So what we see here is that this p-value is above our cutoff of 0.05. It's not significant. So in other words, we see that race does not moderate the relationship between education and whether or not someone is a smoker. So what I typed out here, I said the interaction between race and education was not significant, and then make sure you all always include those p-values. This indicates that being white does not moderate the relationship between a person's education and the likelihood of smoking. In other words, the relationship between education and the probability of smoking does not significantly differ between white and non-white individuals. And then it's also helpful when it says explain, you could say something about the interaction term allowing us to measure differences in groups. So in this case, it's differences based on race, whether or not a person is white. But that would be sufficient for your answer here. Yeah. And then using the model in part E, does being white relate to the likelihood of smoking? Use a likelihood ratio test to evaluate this research question. And what this hint tells us, it says this is a joint hypothesis with more than one equal sign. What this is saying is that we need to impose more than one restriction in the model. So, what we're going to do here, and I also made a note to type out the null hypothesis. I feel like that can be helpful just for reference. So the null hypothesis here null hypothesis is that being white is not related to the likelihood of being a smoker. And it makes sense that we would have more than one equal sign or more than one restriction that we're imposing here because white was included in the model. It wasn't as its own variable, but then also as an interaction. So these are going to be the two variables that we're going to take out in the model that is restricted. So in other words, our null hypothesis here, or our null hypotheses would be, that would be more accurate to say, or that beta 5 equals 0, and then that beta 6 equals 0. And you wouldn't need to type this out or write this out in your answer. It's just helpful for me to write out the null hypothesis and then establish what we're actually restricting, what we're actually testing. So maybe that's just helpful for me. If this isn't helpful context for you, then just ignore it. But we're going to run this likelihood ratio test. So what you would do for that is you would have to establish both models before you run the actual hypothesis test. So it's going to be the same logit model that we ran up here. If it'll let me copy and paste it, that would be helpful. Awesome. So that's going to be our unrestricted model, which is abbreviated as UR. So we're going to run this model and then we will store it by typing out estimates, store UR. And like I said, that just stands for unrestricted. So let's store that in state as memory. And then we will copy and paste this. And this is our restricted model. And we're going to be testing that null hypothesis that I typed out on the other page. So we want to see whether beta 5 and beta 6 are equal to 0. Those are the restrictions that we're going to impose. And so we're going to take out that beta 5 coefficient and beta 6, which are represented by white, and then the interaction term between education and being white. So I'll run this next logit model, and then we're going to store this as the restricted model. That's what this R stands for. So I'll run that, and then to actually run this hypothesis test, then we're going to type out LR test, and then UR and R to actually compare those models. Great. So this is the p-value down here. It's 0.86. And this ultimately leads us to conclude that, sorry, just a second. I got a little bit mixed up in my notes, but essentially what this tells us is that there is not a significant difference between these models, and we would conclude that race doesn't really belong in the model. It doesn't make a difference. It isn't important for the model. Let me make sure I didn't miss anything from my notes, though. Yeah, we failed to reject the null hypothesis that being white is not related to being a smoker. And that was just me rewording it to actually put it in the context of the exact question. So we conclude that being white is probably not related to the likelihood of smoking. And you could type out something or write out an answer similar to this one. Using a likelihood ratio test, I conclude that being white is not related to the likelihood of smoking. You include that p-value, and then say we don't see strong differences between white and non-white individuals in their likelihood of smoking. I feel like talking through this or statistics in general is just saying things a bunch of different ways. So as long as you get across the general idea, then you'll get points. And then this last question, you're just asked to write a short paragraph to explain what we learn about the relationship between macro system factors and smoking behavior. So these are the numbers that we looked at very first in the model, just with cigarette price and the restaurant smoking ban. And if you remember, we learned that cigarette price, or the price of a cigarette pack, isn't significantly associated with whether or not someone is a smoker. And so when talking about like the policy implications of this, I would probably say, yeah, increasing taxes on like packs of cigarettes doesn't really make sense because it's not significantly associated or isn't meaningfully related to whether or not someone's a smoker. However, that wasn't what we saw with the restaurant smoke ban. It looked like people were approximately 10% less likely to smoke if there was a smoke ban. And so it would probably be wise for policymakers in the realm of public health to push for those restaurant smoke bans, and we would probably see a decrease in the number of smokers over time in whichever state that smoke ban is enforced within. So this is just the way that I chose to type that out, but you could give various answers here. Just talk through these numbers and how a policymaker might think about them and what implications they might have. So that is the remainder of question 1 for part 2. And then Julia will make an additional video walking through this moderation problem that'll be posted separately. So thank you so much for joining this review and good luck on your exam. Thank you.